Okay, in this video, we will implement in Scilab the algorithm for Gauss-Seidel, and it follows pretty much these steps. I'm going to go ahead and start up my Scilab. And I'll open up SciNotes. And let's move this down because I want to, I think I'm going to have to make the window a little smaller like that. There we go. And I don't need this. So I want to make some comments in my code that help me design my code according to my algorithm. All right, now whenever you have an algorithm, the first thing you have to do is initialize. Well, what do we need to initialize in this case? Well, we'll need to initialize the matrix A. We'll need C. We'll need N, which is the number of rows of A. And we'll also need an error tolerance because if you remember, we iterate until the error is below tolerance. So I'm going to specify the error tolerance. So let's do that. Why don't I go ahead and use the same A that he does in his second example. One example didn't work, but the other example does work. So we'll use this example here. Okay. So that gives me A is equal to 12, 3, minus 5, semicolon, 1, 5, 3, semicolon, 3, 7, 13. Close it. Okay. I need also C. His C is going to be the constants on the right-hand side here. So it's 1, 28, 76. Okay. And I'm going to do an error tolerance of 0.001. Okay. All right, so let's see where we stand now. We've initialized A, C, and I need the N also. So N is equal to, just like we did in Gaussian elimination, we have to take the size of A, and we want to take the number of rows of A. All right, so our initialization is done. Again, I'm going to do things a little bit different from how he does it. Let's go back up to these equations here that we want to implement. Way up here. All right, here they are. Now, notice that if I put in an initial guess of 0, then all of these terms will go away. And my first estimate for x1 will be c1 over a11. My first guess for x2 will be c2 over a22. So let me write that here. If we say initial guess, and I'll call that x old, because that's going to be my default, my starting guess. So this is going to be all zeros, and it's a vector of zeros. The result gives, this gives x new will be equal to, and I'll write it in Scilab format, this will be c1 over a11, semicolon, c2 over a22, semicolon, all the way up to cn over a n n. Notice that these are simply the diagonal entries of A. I'm taking the vector C and dividing by the corresponding entry of the diagonal, this corresponding diagonal entry of A. Let's see if there's a Scilab function that does that for me. So I'm going to go here and go to my help, and I'm going to look for diagonal. And it looks like there's a command called diag. Let's see what this tells us. It's best to look at the examples. Here it says that diag of the matrix A will give me the main diagonal of matrix A. Okay, so that looks like exactly what I want to get the diagonal elements of A. Okay, so let me go, let me look at this formula here again. This is what I'm going to want for my x nu. The way I can get that is x nu, whoops. Okay, first of all, I need to have my x old is equal to 0. So I'm going to set x, so this is going to be my first pass of the algorithm. I'm going to have x old is equal to 0. Sorry, it's going to be, has to be zeros, and the size has to be n rows in one column. My x nu is going to be equal to c, and I'm dividing component by component by the diagonal entries of A. Now from the tutorial, you should have learned that component by component division is dot slash. And we just learned from the help file that the diagonal entries of A are diag of A. Okay, so this is a component wise division. Okay, so I have my new x. Okay, now let me estimate the error between these two. The error function that I'm going to take is this one here, the maximum of the errors in each component of x. So let me go ahead and do that equation here. I'll make it visible so you can see it. Okay. So my maximum error, still can't see it. Pull it down a little bit. My maximum error is going to be equal to the maximum of the absolute value of x nu minus x old. And that's my maximum error. Okay? So let me go ahead and now, after this first iteration, we're going to loop over all of our iterations. Okay, I've done the first iteration, now I have to do the rest of them. And as we've seen from the document, it's possible that the algorithm won't converge. So we want to limit the number of possible iterations. So I'm going to say 1,000 maximum iterations. A good way to make 1,000 maximum iterations is to use a for loop. And I'm going to let j go from 1 to 1,000. Okay? So I can't possibly iterate more than 1,000 times. Right. So what we're going to want to do now is use these equations, and I'm going to put in my old values of x and update them and get new values of x. Okay. So if I do subsequent iterations, okay. Now, before I start the iteration, I want to store the x I have to start with to compare with my new x so that I can tell what the error is. So the first thing I'm going to want to do is put my current value of x new into x old, and that's my benchmark. After I update all the x's, I'm going to compare with x old and see what changes have happened. So I'm going to say this is my benchmark. Okay. Then we're going to get x new of 1. We'll get that from the first equation. And then we'll do x new of 2 All right. Now you can see that this is also a loop. Okay. So I'm going to have k go from 1 to n here. All right. Now, what's the equation? Well, let's go ahead and set that up, and then we'll talk more about what the equation is. All right. So the first thing I want to do is set x old equals x new, and this is going to be save benchmark value to compare with my or I just say save value to compare with update. And then I'm going to be doing the updates. The update's going to be for k equals 1, 1, n. And this is update variables x1 through xn. Okay. Now, in the update, I'm going to want to get x new of k. All right. If we look at the formula here, you can see the formula here. The form is something like this, parenthesis, c of k minus something. I'm not going to fill that in quite yet. I want to get a good expression for that sum. And then I'm going to be dividing that by a k k. Okay. The problem is getting a good expression for that sum. Let's try to get a handle on what that sum really is. Let's see if I can find some space here. I don't see any good space to do it, so I'm going to open, well, I should scribble somewhere, maybe at the end. We'll just go down to the end. Okay, and you want a expression for if you remember, my update equation is x new of k is equal to c of k minus, and let me write out the sum, what it's going to be. It's going to be a k 1 x new of 1 plus dot 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 plus a k n x new of n, and all of this is divided by akk. All right. Now I've taken care of this. I've taken care of this. I have to take care of this summation here. Notice that the kth term is not included. In this sum. So that's the tricky part. Now, in Gaussian elimination, we had an expression like this, and we expressed this as a matrix product between two vectors. Let's see if we can do the same thing here. What we have here is ak1 all the way up to akn times x new 1 all the way up to x new n. And the only problem is that the k term is not included. Right. Now, this looks very good. This vector here is, in fact, the kth row of A with the diagonal entry set to 0. All right. So if I want to get this sum here, all I need to do is take the kth row of the matrix, multiply it using regular matrix multiplication with my x new, and get rid of the kth term. All right. One way I could do that is I can define, and let me define, I'll define A prime as the same as A A1n. Okay, I define A prime the same as A with the diagonal terms set to 0. Okay, so A prime has zeros on the diagonal. All right, same as A, except the diagonal terms are set to 0. In that case, this product is equal to the kth row of A prime times x nu. So, in summary, AK1 up to AKN times x nu 1 up to x nu n, with k not included, is simply equal to the kth row of A prime times x nu. Okay. So I'm going to have to define this A prime, and once I've defined A prime, then the update will be easy. Okay, so I'm going to have to define A prime in the code. Let me move this up, and we'll see how that works. Now I should define A prime before I start doing the computation, so let me make this big so we can see what we're doing. Right. So let me put it here after I've initialized all of my inputs. So define A prime. Okay. Now A prime is going to be A without its diagonal elements. So A prime. Now remember that diag took the diagonal elements of A and made it into a vector. If you read that help file, well, let's go back there and see. And I read diag about diag again. It says also that if I can say take diag of a vector, if I take diag of a vector, that gives me a diagonal matrix with the entries of that vector along the main diagonal. So I'm going to do something a little bit tricky here. For A prime, I'm going to take A and subtract off the diagonal entries of A, but I'm going to arrange those diagonal entries along the diagonal of a square matrix. So that's going to take out exactly the entries of A that I want. Okay, so this is A with 0 diagonal entries. Okay. That's going to give me exactly what I want. And when we run the code, you'll be able to see that A prime is in fact A with 0 diagonal entries. Okay. Why don't we just go ahead and put that here. So when we run the code, you'll see that A prime does work. All right, so let's go down here. We were stuck at this point, what we were going to put here. Now remember what I said, that this sharp, sharp, sharp is equal to the kth row of A prime times x nu. All right, so at this point, it's not difficult for me to do that. The kth row of A prime is going to be A prime, kth row, whoops, somehow my options changed. I'm going to change my options. I don't want auto-completion. All right, never mind. Minus A prime, kth row is here, and I have my colon, close parenthesis, and now I have a complete statement. And that's all I need to do to update my new, oh, I'm sorry, I forgot to multiply it by x new. All right, so that's all I have to do for my update. Multiply a prime times x new. I'm just doing this equation right here. Okay. So I've finished my update. I put an end there. That ends my for loop. Now, remember that when I go through all of my, when I update all the variables, now I want to check and see if the error is below my tolerance. So here I'm going to check if error is below tolerance. So let me define max error. That's it's the same equation as above. So I could just take this and copy it, and I'll paste it here. Now, if the maximum error is small, then I want to stop my procedure. So if max error is less than error tolerance, then, and the way to stop my procedure, the command is called break. And then here I put an end. Okay. And that's the end of my loop, so I put an end here. And then my result should be in x new, so I'm going to put display x new. Okay. All right, let's cross our fingers and see if this works. So we'll go ahead and, okay, so let's save and execute. And I'm going to call that this here. This is my Gauss seidel. And let's see what it gave me. I have to go to my console window. All right, here we've got our, this was A prime, and notice that it is in fact A with zeros on the diagonal. And here is our answer, very close to 1, very close to 3, very close to 4. And you can verify that that is indeed the correct answer. Okay.